Now in this video we're going to be talking on the preparation of alkanes from alkyl halides. Now alkanes can be prepared from alkyl halides through four different methods. The first method is by the reduction of alkyl halide, the second is Wurtz reaction, the third is Franklands reaction, and the fourth is House synthesis. Now we're going to be talking on the first one immediately. Now the first one, like I said, is by the reduction of alkyl halide. Now this is the most common method of preparing alkanes from alkyl halide. Now I'm sure we all have heard of this. Now the alkyl halide is reduced to alkane by reacting it with hydrogen gas in the presence of zinc metal to yield an alkane. Now there's something we need to note, like we need to reduce it. Like from the name, we all know that reduction is like the addition of hydrogen from our definition of reduction. So it occurs in the presence of zinc metal. Zinc metal acts as a catalyst to this reaction and end up yielding an alkane and hydrochloric acid, or it can be any acid. It can be hydroiodic acid and so on, hydrobromic acid, depending on the halide present. Now this reaction, I don't need to thoroughly give you an example or so forth of this reaction because I'm sure you all get it from here. Now the second is Wurtz reaction. Now this method is used to prepare higher alkanes. Alkyl halide is reacted with sodium metal in ether solution. Now this is the thing you need to know whenever you're talking about Wurtz reaction, because this alkyl halide it's a constant in all of this reaction, but it's now like the different reagent that they're going to react it with. That's like the difference in all of this reaction. Now alkyl halide is reacted with is heated with sodium metal in ether solution, which will result in the production of alkanes. Now 2 moles of alkyl halide is needed, and the reaction mechanism is a free radical mechanism. Now, like the first point I gave, I said this method is used to prepare higher alkanes. Now, reduction of alkyl halide is only used to prepare lower alkanes. You can't use it to prepare higher alkanes because when you go higher in the homologous series, you find out that the reaction ends up not becoming feasible. And now the reaction is a free radical mechanism. That's the last point I gave. Now the equation of the reaction is given below. I said 2 moles of an alkyl halide react with 2 moles of sodium and ether is present, and this will yield to the formation of an alkane and sodium halide. Now let me just write that reaction again because I need to give the general equation of the reaction before we go down to the mechanism. I will explain it. Now, like I said earlier, 2 moles of an alkyl halide will react with 2 moles of sodium in the presence of ether, and this is going to yield an alkane and sodium halide, 2 moles of this. Now, like I said earlier, the reaction is a free radical mechanism reaction. Now we need to note something, that this sodium we're actually using is in its radical form. It's not actually in its, let me just say, atomic form. It's in its radical form. So let's go for now this Rx it's going to split, it's going to fuse homolytically, and therefore this will end to the formation of radicals, and we have something like an alkyl radical will be formed and a halide radical will also be formed. Now these 2 radicals will be formed. Now what is actually going to happen is that since there are 2 moles of these alkyl halides here, so we are actually going to have 2 moles of this alkyl radical form and 2 moles of this halide radical form. Now these 2 moles of the alkyl radical, will actually fuse together. We have something like this and something like this. And we all know that when 2 radicals combine, they end up forming a bond or an electron, and we have something like this, and a bond is formed between them. So this is what is actually going to happen between them, and this is actually the alkane that we're actually going to form. Now we find out that the alkane is actually higher than the alkane formed is actually higher than the primary alkane we use, if I call it that. The alkane form is higher than the primary alkane we use. That's why it's used in the formation of higher alkanes. Now we can also talk about how the sodium halide is formed, but we don't really need to, but let me just talk about it. Now, like I said, the sodium is in its radical form and is going to react with 2 moles of the halide radical, and this will yield to the formation of NaX. Now 2 moles of this. Now this is just like the overview of the reaction. Now all we just need to note is this, and we are safe to go. Now the next reaction we're going to be talking of is the Franklands reaction. Now, this method involves reacting alkyl halides with zinc in the presence of an inert solvent. Like I said, alkyl halide is like a constant in all of this reaction. All we need to note is that the changing, or what should I say, the varying factor is now the reagents that we're going to be reacting alkyl halides with. Now, inert solvents could include benzene, toluene, dichloromethane, and so on. Now, like Wurtz reaction, 2 moles of the alkyl halide is also needed, and it's also used in formation of higher alkanes. So we have 2 moles of the alkyl halide plus 2 moles of zinc in the presence of an inert solvent, and this is going to yield an alkane and zinc halide. Now we find out that this is like similar to the Wurtz reaction, but the major difference between these two reactions is the mechanism which it will follow. Now, Franklands reaction will yield to the formation of an organozinc intermediate compound. Now, that is just like the major difference between these two reactions and the reagents, obviously. So we have Rx, we have Rx. Like I said, 2 moles of it is going to be present. I don't want to start decoding for you, so let's just go. 2 moles of this is going to be present, reacting with 2 moles of zinc, and this will yield to the formation of plus. Oh, if I want to actually balance this, I don't need to actually impute my 2 moles of zinc. So this is what is actually going to be formed. Now, like I said earlier, this is going to yield to the formation of an organozinc compound. So in the mechanism of the reaction, in the mechanism of this reaction, an organozinc compound is going to be formed, and how that's going to be formed is an alkyl halide. 1 mole of an alkyl halide is going to react with zinc, and this will yield to the formation of the organozinc compound. Depending on the alkane present or the halide present, that's how we are going to like form it. So if I'm just like giving a general name, I can call this an organozinc compound, and that's what I'm just calling it. Now this is the intermediate formed. Now this intermediate, 2 moles of it, 2 moles of this intermediate will actually decompose, and it will yield, and it will yield a dialkyl zinc. If I put it that way, it will yield a dialkyl zinc compound and zinc halide. Now, if we see from this equation of the reaction that this is another intermediate formed, this dialkyl zinc compound is another intermediate formed. The first intermediate formed, like I called it, is an organozinc compound. Now, these 2 moles of this organozinc compound will actually react to form a dialkyl zinc, and this dialkyl zinc formed will now react with an alkyl halide, like another alkyl halide, because all of these are in a solution. So there are different like molecules of alkyl halide in that solution, different molecules of this dialkyl zinc in that solution. So they will actually react, and it will lead to the formation of an alkane plus another alkyl halide. Now if I can put this, no, don't worry. So I have this 2 moles of this present too. I can put 2 moles here. RR plus ZnX2. Now, as we've seen from this, like from the 3 equations, let me just give them, or let me just number them. This is the first equation, this is the second, and this is the third equation. So we can see this is a 3-step equation. Like this is a 3-step equation mechanism. The first equation, like I put earlier, is the reaction of the alkyl halide with zinc, and this will lead to the formation of an organozinc compound, and that's the RZNX. And this RZNX, 2 moles of it will actually decompose and will yield to the formation of dialkyl zinc plus the zinc halide, and also this dialkyl zinc will now react with an alkyl halide, and this will lead to the formation of an alkane and another zinc halide also. Now let's go to our next what should I say, our next type of reaction. Now this is the Corey-House synthesis. Now this involves the reaction of alkyl halide with an organocopper reagent called lithium dialkyl copper. Now, like the first one, don't mistake them. They are different. This is an organocopper reagent, and the name of that organocopper reagent is the lithium dialkyl copper, and this is also called Gilman's reagent because it was actually discovered by Gilman. Like the reagent, this lithium dialkyl copper was actually discovered by Gilman, and scientists tend to name things after themselves. So let's go on. Now the lithium dialkyl copper. Now we're going to be looking on how we're going to be preparing this lithium dialkyl copper before we are able to react it with an alkyl halide and then forming our alkanes. Now the lithium dialkyl copper can be prepared by reacting an alkyl halide with lithium metal, leading to the formation of an alkyl lithium. Now the first thing first that we need to do, we have to react an alkyl halide with a lithium compound, and that will lead to the formation of an alkyl lithium. So like we can see from our equation of the reaction, 1 mole of an alkyl halide is reacting with 2 moles of lithium, and that will lead to the formation of the alkyl lithium. That is this, and then lithium halide. Now this alkyl lithium formed, it's going to actually be used in the second step of the reaction to actually form the lithium dialkyl copper. And now the second step of the reaction involves reaction of alkyl lithium with copper 1 iodide, leading to the formation of an organocopper reagent. And this is the organocopper reagent. Now we can actually call it lithium dialkyl copper, but in general you can just call it an organocopper reagent. So we have the 2 moles. Now 2 moles of this alkyl lithium will react with copper iodide. Remember, it's copper iodide, not just any other copper that you think of. Reacting with copper iodide is not just any other halide that we think of, is copper iodide in general. Now we have 2 moles of this alkyl halide. 2 moles of this alkyl lithium will react with 1 mole of copper iodide, leading to the formation of the lithium dialkyl copper and lithium iodide. Now that's just like the full thought. Now let me just go further. The Gilman reagent produced is then reacted with an alkyl halide or an aryl halide to produce an alkane. Now we can see from this equation of the reaction that the Gilman's reagent produced, that let me just call this Gilman because it's better than calling it lithium dialkyl copper, that's too long. So it's then reacted with an alkyl halide. Now this alkyl halide can be any other form. You can actually use the first one you used before. You can actually use an alkyl halide to lead to the formation of an alkane, and one alkyl group will actually be lost in this reaction, and that alkyl group will actually combine with the copper and will form an alkyl copper, and then a lithium halide will actually be formed. Now we can see from this equation, it's not actually a hard reaction, it's just self-explanatory. This equation of the reaction is just for you to know the intermediate form. Now we need to note something about Corey-House synthesis. Corey-House synthesis is a more efficient way of preparing alkanes than Wurtz reaction. It's a more efficient way of preparing alkanes than Wurtz reaction. Just note that. And the reaction is an example of a cross-coupling reaction. Now, a cross-coupling reaction is a type of reaction whereby 2 or more fragments or species are joined by the aid of a metallic catalyst. Now we can see from this that the metallic catalysts include the copper and the lithium, but yeah, those are the metallic catalysts. Now what is actually happening here is this mole, let me just now label them so I can actually explain it better. Now 1 mole of this, let me just put it, 1 mole of this alkyl group can combine with any, like I said earlier, it can combine with any type of alkyl group present. It can combine with, let me just say another one, let's call it R prime. I'm not going to give you an example, I hope you can understand it from this. So let's just go, can combine with this and it will lead to the formation of this. And this, when this happens, it is actually called cross-coupling. And that's why I called it a cross-coupling reaction. It's not a hard stuff. Now, because of the presence of the copper and the lithium in the first mole of like the lithium dialkyl copper, like this, that will act as a catalyst to yield to the formation of this. So, like I said, 1 mole of the alkyl from the lithium dialkyl copper is actually going to be lost in the formation of alkyl copper. But just note that 1 mole of this alkyl from the lithium dialkyl copper must combine with the other alkyl from the alkyl halide to yield to the formation of this alkane. present. So that's it's all. Thank you for viewing. Please like and subscribe to my channel. Thank you.